Every single day, you probably use language without giving a second thought to its intricate, almost magical architecture. It just works, right? But what if we told you that the way you construct a sentence, the way you understand a single word, even the way you make a sound, all follow a sophisticated, layered blueprint? And here's where it gets really interesting. What if this isn't just a dusty old theory, but a profound design principle that cutting-edge AI models are, well, accidentally rediscovering, mirroring the very structure of our own brains? In this deep dive, we're going to pull back the curtain on the fascinating concept of linguistic levels. We'll explore how classical linguists meticulously identified these hidden layers, then how modern artificial intelligence is now showing us these layers can spontaneously emerge on their own, and what this surprising convergence tells us about language, intelligence, and, even ourselves. Get ready for some serious aha moments that might just change how you think about every word you utter. To guide us, we're pulling from a fascinating combination of sources. Foundational works from classical linguistics, including a significant collective study from Moscow back in 1972 on language's internal structure, and also a really insightful recent interdisciplinary analysis that bridges these classical ideas with modern AI titled The Convergence of Language Systems, Parallels Between Classical Linguistics and AI Language Models. Okay, let's unpack this. For decades, linguists have understood language not as a flat entity, a simple string of words, but as a complex multi-level system. What exactly does that mean when we talk about language having layers, and what are these foundational ones?
That's a great place to start. Traditional linguistics refers to these as layers of language or levels of language structure. It has been a central problem in understanding how language actually works. The core idea is that language is built up, almost like a complex building, from distinct but interconnected levels. These levels often correspond to specific linguistic disciplines you might already be familiar with. We begin with phonology, the study of the smallest sound units, what we call phonemes. Think of the individual ku sound in cat. Then there's morphology, which looks at meaningful word parts, or morphemes, and how they combine to form words, like unable in unbreakable. Next up is syntax, which governs how we arrange words into phrases and sentences, the grammatical rules that make sense of it all. We also have lexicology, which is, well, simply the study of words and vocabulary, and word formation, exploring how new words are created from existing ones, and finally phraseology, which delves into fixed expressions and idioms like kick the bucket.
So it's definitely not just a random list of components, is it? You mentioned a hierarchy earlier. How do these layers fit together in a specific, organized way?
Precisely. They are hierarchically organized, meaning that units from a lower level typically combine to form units of a higher level. Think of it like building blocks or perhaps like a pyramid. Individual sound units, phones, combine to form those meaningful parts of words, morphemes. Then morphemes form words, and words then combine to form sentences. Leading linguists like Charles Hockett mapped out these intricate relationships, showing how even morphemes break down into smaller sound components. This fundamental structure helps us distinguish between the system, the overall wholeness of language and structure, the specific connections and arrangements of its elements. And these elements relate in two crucial ways. Syntagmatically, which is how words appear in linear succession, like the cat sat on the mat, where each word follows the other. And then paradigmatically, which refers to the choices you make from alternatives that could fit in that same spot, like choosing the cat slept instead of the cat ran.
Ah, okay. So it's the difference between what is there and what could have been there.
Exactly. That distinction really helps clarify it.
This really shifts our perspective on language, but is this layered structure static, or is language always in flux, adapting and changing?
That raises a critical point. While these distinct levels exist, there's also a dynamic interdependence, sort of an internal solidarity among them. The internal structure of language is far from static. It involves continuous processes where new elements emerge and old ones disappear. Modern linguistics recognizes this incredibly dynamic nature, moving beyond mere static descriptions to account for the constant evolution and adaptation of language systems.
Right, like how slang emerges or how words shift meaning over time.
Exactly. Those aren't isolated incidents, but part of this dynamic interaction across all levels.
So we have this incredibly rich, layered understanding of language from classical linguistics, meticulously identified over decades. Now, for the curveball, what does any of this have to do with artificial intelligence? Are machines somehow replicating this deep structure, or is it just a coincidence?
What's truly fascinating here is the concept of emergence. In modern AI models, these linguistic hierarchies aren't explicitly programmed by engineers or linguists, not usually anyway. Instead, they spontaneously arise as a result of the model training on absolutely massive amounts of text data.
Just from the data itself.
just from the data. It's an accidental yet profound rediscovery of what human linguists have theorized for decades. These models essentially figure out the layers for themselves without anyone telling them to.
That's genuinely wild. Can you give us some examples of how these hierarchies manifest within these AI systems?
Absolutely. We see this in, well, two key ways, depending on the specific architecture of the AI. First, in what are called multi-timescale recurrent neural networks, or MTRNNs, we observe a fascinating temporal hierarchy. Imagine neurons in an AI network operating at different speeds, some reacting incredibly fast, others much more slowly. In MTRNNs, deeper layers react quickly to short-term patterns, while higher layers respond slowly to long-term contexts.
So different speeds of processing. How does that organic distinction map onto the language layers we just discussed?
The parallels are striking. The very short timescales, processing individual sounds or brief word fragments, capture rapid, local processes. This corresponds to things like phonological features distinguishing between a B and a P and basic letter-to-sound mappings.
Okay, the really fine-grained stuff.
Exactly. Then you have medium timescales, handling phrases or short sentences, which encode morphological and syntactic structures, like understanding verb tenses or noun-verb relationships. And finally, long timescales, sometimes spanning entire paragraphs or even documents, capture extensive connections, responsible for lexical and semantic coherence across much larger texts.
So the model organically figured out that different aspects of language need different processing durations. Is that the essence of self-organization at work here?
It really seems to be.
And what are its broader implications? Does this tell us something fundamental?
I think it does. It suggests a fundamental principle. For a system to efficiently process highly complex information like language, it needs specialized components operating at different scales. This isn't just about language. It's a blueprint for any complex information processing system, whether it's understanding stock market fluctuations or even how a massive organization manages projects.
And what about those big, powerful transformer models we hear so much about, like Google's BERT? Do they also show this layering, or is their architecture fundamentally different?
Oh, they absolutely do. But perhaps in a more architectural sense, rather than purely temporal, research using probing classifiers.
Right, those tools that let you peek inside the model's brain.
Exactly. They reveal a clear functional pipeline across BERT's various layers. It's much like the classical natural language processing pipeline that linguists developed. The layers specialize in different linguistic tasks as information flows through them.
Can you walk us through that internal pipeline? What's happening in those different layers?
Certainly. In transformer models like BERT, the early layers, typically layers 1 through 3, are processing surface features. They handle low-level linguistic tasks such as basic phonological processing, morphological segmentation, essentially recognizing prefixes and suffixes like un or ing and identifying basic word boundaries. They're establishing the raw inputs.
Okay, the basics.
Then, as the information moves into the middle layers, say from 4 to 8, the model specializes in syntactic structures. This is where it starts to build phrases, understands grammatical relations between words, and manages dependency hierarchies, figuring out which words modify or relate to others. It even codes for complex phenomena, like subject-verb agreement across longer distances in a sentence.
So grammar, basically.
Essentially, yes. Finally, the late layers, usually 9 through 12, focus on semantic composition and lexical semantics. Here, the model is determining the nuanced meaning of words in context, resolving ambiguities, and ensuring overall text coherence and discourse understanding across larger passages.
Getting at the actual meaning. So information flows from simple sound and word recognition to complex meaning, almost like a direct architectural implementation of what linguists have always described. It's astonishing that these models figure this out without explicit instructions, without us explicitly coding this layer does syntax. It just emerges.
It really does. It emerges from the patterns in the data.
Okay, this is truly mind-blowing. AI models are spontaneously developing language layers, strikingly similar to what linguists identified, often without being explicitly told to. But what about our brains? Do we process language in these same kinds of hidden layers?
Well, if we connect this to the bigger picture, the parallels extend even further to human neurobiology. Neuroscience has established what's called a dual-stream model of language processing in the brain.
Dual stream, okay.
Yes, and it's another powerful example of hierarchical organization, echoing what we see in linguistics and AI.
Tell us more about these two streams. How do they divide the labor of language processing?
So there are two main processing pathways. The dorsal path is primarily responsible for auditory motor integration. This means it links the sounds we hear to the actions needed to articulate them. It's crucial for tasks like repeating speech, organizing sequential elements of language, and essentially how we translate heard sounds into our own spoken words. Think of it as the how to say it pathway.
The mechanics of speaking.
Right. The ventral path, on the other hand, is responsible for auditory conceptual integration. This pathway maps sounds directly to their meanings. It's essential for language comprehension and semantic processing, handling the higher-level aspects of language, helping us understand what words, sentences, as entire conversations actually mean. This is the what it means pathway.
Got it. Sound to meaning.
Exactly.
So in essence, the brain has its own fast and slow lanes, or its early and late layers for different aspects of language?
That's a great way to put it. The phonological and morphosyntactic tasks of the dorsal path mirror the functions of BERT's early to middle layers and MTRNNs, short to medium timescales. Conversely, the semantic and discourse tasks of the ventral path find their analogy in BERT's late layers and MTRNN's long timescales.
Wow, the parallels are really strong.
They are. And EEG studies even show our brains process different linguistic timescales in parallel. For example, a very quick, say, 100 millisecond window for phonemes and a longer 600 to 900 millisecond window for syntactic integration.
So it's all happening at once, but on different tracks.
Precisely. This convergence across classical linguistics, cutting-edge AI systems, and our own biology suggests that hierarchical organization isn't just a good idea. It seems to be a universal and necessary principle for efficiently processing something as complex as language. It's how complex systems manage, understand, and produce incredibly intricate information.
This convergence is absolutely remarkable. What does this all mean for our understanding of language and intelligence, particularly as we look at the capabilities and limitations of AI? What can these LLMs teach us about ourselves?
That's a truly important question. What can large language models, or LLMs, teach us about how humans learn and process language? Well, one significant implication is the validation it offers for usage-based theories of language acquisition.
Ah, the old nature versus nurture debate for language.
Kind of, yeah. For a long time, there's been this debate. Does language come from an innate generative grammar hardwired into us, or from usage-based learning, simply by interacting with and analyzing the language we hear? The spontaneous emergence of complex grammar in LLMs, purely from statistically analyzing massive text, strongly supports the usage-based theory. These models learn grammar from language use itself, demonstrating how purely statistical regularities, when processed at scale, can lead to incredibly sophisticated structural complexity without any explicit rule programming.
So it suggests our brains might be doing something similar.
It certainly lends weight to that idea, picking up patterns from the language we encounter, rather than starting with a complete rule book downloaded at birth, so to speak.
So it's a powerful argument for learning by doing, by exposure. But surely there are crucial distinctions between how an LLM understands language and how a human does. Where do the limits and fragility come into play?
Absolutely. While powerful, LLMs generalize through what we might call analogical thinking over stored examples, not by forming an abstract symbolic mental dictionary or a flexible rule-based system like humans seem to do.
Analogical thinking, like finding similar patterns.
Exactly, which leads to what's described as surprising fragility. For instance, a minor syntactically correct change in a prompt can sometimes cause a drastic performance drop in an LLM, leading it to generate nonsensical output.
Right, I've seen examples of that, things that wouldn't trip up a human at all.
Precisely. It indicates a fundamentally different internal representation. LLMs are master statisticians, predicting the next most probable word with incredible accuracy based on patterns they've seen billions of times. But they may not yet reach the level of true symbolic abstraction that gives human language its deep robustness, flexibility, and, well, common sense understanding.
So it knows that the cat sat on the mat is likely.
But it doesn't picture a cat or understand the concept of sitting in the way you or I do. It's a profound difference, at least for now.
So what stands out to you for our listener from all of this? Why should you care about these hidden layers, whether they're in your brain or a machine?
What's truly fascinating here, I think, is the sheer power of organization. Whether it's ancient human theories, modern AI, or the biological machinery in our heads. The most efficient way to process something as complex as language seems to be through these distinct yet interconnected hierarchical layers.
It's a recurring pattern.
It really is. And this isn't just about how we talk or how machines process text. It's a universal blueprint for any complex system, from building a successful company with specialized departments to even organizing your personal workflow. It shows that breaking down information into specialized hierarchical parts is incredibly efficient for managing complexity and extracting meaning.
It's almost like the universe is whispering the same design principle across vastly different domains of intelligence.
That's a nice way to put it.
We've taken a deep dive into the hidden layers of language, tracing their understanding from classical linguistics, through the emergent structures and cutting-edge AI models, and finally into the very architecture of our own brains. It's a remarkable story of convergence, showing how different forms of intelligence, whether human, biological, or artificial, arrive at similar, efficient solutions for handling the incredible complexity of communication.
Yeah, this universal emergent principle of hierarchical language organization isn't just an academic curiosity. It underscores that structure isn't just a human invention. It's fundamental to how complex systems, natural and artificial, process information, making it more efficient and robust. It's a testament to the power of breaking down complexity into manageable, interconnected parts.
Which leaves us with a big question, doesn't it?
It does. So what does it truly mean that AI can mimic our linguistic abilities so well without necessarily having the same abstract symbolic understanding? Are we witnessing the birth of a new kind of intelligence that simply needs enough data to figure out the rules of language and achieve mastery? Or does true language mastery for any intelligent entity require a leap beyond statistics to deeper symbolic thought?
And if so, what might that deeper universal language of thought truly be, and can we ever build a machine that speaks it?